please go ahead.
Great. Okay, I will start sharing my screen. All right. So if I'm correct, you're now able to see the presentation. Is that true? Excellent. Okay. Yeah, thank you so much for having me. I am Samuel, as I just been told. I study at the University of Oxford, where I research quantum information in the group of Vlatko Vedral. And today I would like to talk about my research on non-commuting qubits with an application to the closed time-like curve problem. And I would like to start the talk with a problem that I think deserves attention in physics. And that problem is caused by something called the commutation constraint, or so I called it. So the commutation constraint in quantum theory is the assumption that the observables of systems at space-like separation commute with one another. And this is an axiomatic element of quantum theory. In fact, I will say it's an axiomatic element of what I'll call orthodox quantum theory, which is the conventional theory. And one of the reasons for this assumption being there is that it ensures quantum theory satisfies Einstein's criterion of locality, that the real factual situation of a system A is independent of what is done with a system B, which is spatially separated from the former, where for one thing, although this is indeed a consequence of the assumption, it's not a necessary requirement for quantum theory to adhere to Einstein's criterion. And moreover, it causes all kinds of issues. One of these issues is that, for example, in quantum field theory, the Hilbert space associated to a finite region of space, such as R, necessarily has an infinite dimensional Hilbert space, because field observables at space-like separation have to commute according to the commutation constraint. And to accommodate, so there are infinitely many space-like separated events in a region such as R, meaning that there's infinitely many of these commuting observables, and to accommodate those infinitely many commuting observables, the Hilbert space has to be infinite dimensional as well. Yet there are good reasons for believing that the Hilbert space of a region such as R should be finite dimensional, because otherwise the entropy of R is unbounded, which would conflict with Bekenstein's formula. That particular point was discovered by Powell, Carroll, and Singh, which was very nice. As a consequence of this, Deutsch has proposed in 2004 an alternative quantum field theory called qubit field theory, which has the properties that its field observables do not necessarily commute at space-like separations, and which has a finite dimensional Hilbert space. And Deutsch has conjectured that these qubit fields satisfy Bekenstein's bound, but that remains an unproven conjecture, because we lack the necessary theory of information for qubit fields. We don't know whether those fields can store or retrieve information. A second problem that the commutation constraint causes is that it cannot be satisfied when space-time cannot be foliated into space-like hypersurfaces. So the assumption that goes into the commutation constraint is that space-time necessarily can be foliated in space-like hypersurfaces, but that's not necessarily true when space-time contains non-chronal regions, like in the Kerr metric, in the Gödel metric, or space-times with reversible wormholes. And this is a problem even if those space-times turn out to not be instantiated in the physical universe, because general relativity does not necessarily need space-time to have foliations into space-like hypersurfaces, where apparently the commutation constraint, which is axiomatic in quantum theory, in what I will call orthodox quantum theory, does require that such space-like foliations, into space-like hypersurfaces exist. So this is an a priori incompatibility between orthodox quantum theory and general relativity. And I think because of these two problems, we should investigate quantum theories without the commutation constraint. Also, I should add that even if, for example, you impose that the commutation relations between space-like separated systems is different. So, for example, if you impose that the commutation relation between space-like separated systems is that they have anti-commuting observables. Even then, you run into problems because that is again assuming that space-time can be foliated into space-like hypersurfaces. So we should, but I will, in particular, I will focus on this commutation constraint, and we should investigate quantum theories without the commutation constraint. For example, we should have a discrete version of Deutsch's qubit field theory, a theory of non-commuting qubits, of qubits that don't commute at space-like separations. And if such a theory of non-commuting qubits turns out to be universal in the sense that such non-commuting qubits can simulate with arbitrary accuracy any other physical system, then they might be used to model general systems on closed time-like curves. So to that end, I want to consider an array of n qubits and non-commuting qubits, which, following Deutsch and Hayden, will be represented as a triple of observables at any time t, where these observables are, of course, omission and also obey the Pauli algebra. And conventionally, we would now impose that these qubits have observables that commute at space-like separations, but here I'll treat the more general case in which we don't assume their commutation relations. Now, to investigate the dynamics of such non-commuting qubits, we find that by imposing each qubit adheres to the Pauli algebra, they have to evolve unitarily. But because a global unitary would not preserve Einsteinian locality, I will assign potentially different unitaries to each qubit. So to a qubit QA belongs a unitary U of A, which uniquely specifies how that qubit evolves. And where you can see that this theory is locally realistic in the sense that you can assign to all qubits but qubit A a unitary which is identical to the unit observable. So those qubits do not evolve, whereas the unitary of UA of qubit A is some non-trivial function, and therefore only only qubit A evolves, where all the other qubits remain stationary. So individual operations can be performed in the qubits. And of course, by definition, these unitaries adhere to the algebraic identity shown below. Now, just as to each qubit belongs a unique unitary, each qubit also has a unique so-called generator of motion, which is similar to the Hamiltonian in orthodox quantum theory. These generators of motion are defined in terms of the derivatives of the unitaries. And because of that, they are necessarily Hermitian, but they are not necessarily constants of the motion, because their evolution depends not just on themselves, but also on the evolution of all of the other generators in the array, of which there are n. And I also impose the additional physical constraint that the generator of motion, or rather that each generator of motion in the array is a function of the array's observables. So, for example, it is not a function of time. It's not an explicit function of time. And by specifying what the generators of motion are, you can also deduce what the unitaries must be, because the unitaries can be expressed as a time-ordered product of these Hamiltonians, of the integral of these Hamiltonians. Oh, sorry, I should call them generators of motion. That's my mistake. So you can express these unitaries as a time-ordered product of the generators of motion. So as I said, the individual unitaries preserve the algebraic properties of qubits in isolation. And I think it's worthwhile to go through a brief couple of lines to show that this is in fact the case. And the way that that can be done is by considering the product of two qubit observables of the same qubit QA at time t, and expressing those observables in terms of the observables at time t equals 0, conjugated by that qubit's unitary UA. Then simplifying the equation by using the identity that the Hermitian conjugate of the unitary times the unitary itself is the identity, and then inserting the algebraic relations at time t equals 0, we find that the qubits at time t must also adhere to the Pauli algebra. So showing that indeed the Pauli algebra is a constant of the motion for each qubit. However, the algebraic relations between qubits in such an array will typically vary with time because they are assigned potentially different unitaries. And in the conventional theory, in orthodox quantum theory, the algebra of a quantum system is a constitutive property, meaning that you can use it to distinguish two systems from one another. So how would you distinguish one array of non-commuting qubits from another array? In other words, in what sense does the array retain its identity while it evolves? Or what Popper called the problem of change, which he formulated nicely as, how can a thing change without losing its identity? For non-commuting qubits, we can define a vector space O of all Hermitian operators that can be constructed additively and multiplicatively in terms of the observables of individual qubits. And it turns out that this vector space at a time t equals 0 has a basis which is also a basis for the vector space at any other time, meaning that this vector space is a constant of the motion. So by completely determining what this vector space is, we can then assign at any later time to the qubits particular elements of O, and in that way we completely specify the array in all its possible states. In other words, the characteristic property of the array is this vector space O, and it can be used to distinguish this array from another array of non-commuting qubits. Now, importantly, the vector space O has a subspace OA spanned by the observables of a particular qubit, in this case, QA. And whereas in the conventional theory was an orthodox quantum theory, the intersection of two subspaces OA and B and OB is necessarily 0. In the non-commuting case, these subspaces might have some overlap, meaning that some of the observables of a qubit QA can be expressed as linear combinations of the observables of qubit B. And a boundary case of this is when the qubits maximally non-commute, meaning that all of the observables of qubit A can be expressed as linear combinations of the observables of qubit B and vice versa. In other words, it's when these subspaces have overlap, have complete overlap, they're identical. Now, 2O belongs to an n-dimensional Hilbert space, H, and the observables of O can be expressed as n-dimensional matrices on that space. And because of the fact that the subspaces of particular qubits might overlap, the Hilbert space, H, is not necessarily a tensor product of the two-dimensional Hilbert spaces belonging to each qubit, meaning that the dimension of the Hilbert space is typically smaller than it would be if qubits do commute. This also means, as it turns out, that the number of parameters necessary to completely define the array is smaller than it would be in the orthodox case, in the case in which qubits commute. And a way to show this is by considering an array consisting of n maximally non-commuting qubits, meaning that such an array has a two-dimensional Hilbert space, the smallest it can be for an array of n qubits. And by then realizing that each of the observables of the individual qubits can be represented as some linear combination of the Pauli matrices. The most general such linear combination is a rotation about 3 axes, represented by the angles theta, phi, and psi. And that means that to fully specify this array, I just need to specify 3n parameters. Whereas to similarly specify the observables of an array of n commuting qubits would require 2 to the 2n minus 1 parameters. And this means that maximally non-commuting qubits apparently contain exponentially less quantum information than their orthodox counterparts. Finally, to completely specify the state of the array, we should also talk about the Heisenberg state, which is array in Hilbert space. And because the Hilbert space is a constant of the array, so is the Heisenberg state. And I shall fix the Heisenberg state to make it a standard constant by imposing that the Z observables at time t equals 0 all have the definite value 1, which means that the Heisenberg state is the eigenstate of these Z observables up to some irrelevant phase vector. So the term Heisenberg state becomes somewhat of a misnomer because no information about the actual state of the network is contained in the Heisenberg state. And finally, I will denote the expectation value of an arbitrary Hermitian operator, A hat in O, as follows, just as a shorthand. So now we have kind of the foundations of a theory of qubits that do not necessarily commute with one another, which is a locally realistic theory in Einstein's sense, although not necessarily in Bell's sense. It might be Bell non-local. And I would now like to talk about specific gates and how to implement gates, and then move on to a paradox using a closed time-like curve and sort of showing how these qubits can be used to alleviate the paradox. So gates, unlike in the previous sections in which I talked about qubits evolving continuously, gates are implemented during periods of fixed duration, conventionally assumed to be 1 unit of time. And a gate is implemented by a set of generators of motion that act during that fixed period. So within the fixed period, the qubits evolve smoothly, and then at the end of the period, they might change discontinuously when you change the interactions. For example, the effect of a gate G implemented between times t equals 0 and t equals 1 is defined by a characteristic set of generators of motion shown below. And because I specifically want to talk about classical information, I would also like to introduce the notation where the possible states for which a qubit has a Z observable that has a definite value either 1 or -1 are shown to be these 1 check subscript A and -1 check subscript A, meaning that so those are the states for which the qubit has a particular definite value. And a classical gate I will define as something which takes as an input one of these definite values and outputs another definite value. So for example, we have the NOT gate, which is implemented during the period starting at time t equals 0 and ending at the time t equals 1. If the generator of motion of the qubit on which the NOT gate is applied to is equal to a rotation about that qubit's x-axis by pi radians, where all the other generators of motion are set to 0. So only this particular qubit remains, it evolves, and all the other qubits are constant. They're stationary. And the effect of this gate can be expressed algebraically by writing the observables at time t equals 1 in terms of the observables at time t equals 0. And it turns out that the Z observable of the qubit is toggled. So if you input the initial state where the qubit has value 1, it will become a -1. And if you input the value -1, it will become a 1, as shown at the bottom of the slide. Now, a second important gate is the C0 gate, which is implemented on a control and a target qubit, which again, these might not necessarily commute with one another. And the effect of the C0 gate should be that it performs the operation where a NOT is performed on the target qubit if the control has value -1, and a unit wire is performed on the target qubit if the control has value 1. So again, that is shown below. Now we know how to perform this gate when we have the commutation constraint, but when we lack the commutation constraint, it's very difficult to implement this or to find a particular interaction that allows the qubits to evolve so as to enact this transformation. The reason for that is if you write products of two observables of two maximally non-commuting qubits, then you can always rewrite those products in terms of the observables of just one qubit, because of course when qubits maximally non-commute, their observables can by definition be expressed as linear combinations of one another. And it turns out that to circumvent this problem, we have to introduce a so-called reference qubit with particular properties. Specifically, the reference qubit will have to have initially the definite value 1, and it will have to maximally non-commute with the control qubit, such that we can consider a particular superoperator, which takes as input the Z observables of the control and the reference, and which then outputs a function which depends on the anti-commutator of the Z observables. And as I said, because these qubits maximally non-commute, it turns out that you can actually rewrite this expression in terms of something that depends explicitly on the expectation value of the Z observable of the control. So using this reference qubit and the superoperator that we can construct from it, we can write down the following generator of motion for the C0, which if we reduce the expression, so first of all, the first line is a legal expression because it depends only on the observables of the network, and the second line is simply reducing the expression by using the specific properties of the reference qubit. Then we can see that if the control initially has definite value 1, the generator of motion will reduce to 0, and if the control has definite value -1, then it will reduce to a NOT gate as required. And again, all the other generators of motion of the other qubits, so of the control and the reference qubit, are kept to be 0, so those qubits are stationary. And in that way, we find that we can implement a C0 on these qubits. And in fact, this procedure can be extended to also create a CC0 gate, meaning that you can basically perform any classical reversible computation on the network. So having this understanding of the foundations of the theory and also showing that we can enact certain gates, I would like to now cover the paradox using a closed time-like curve. So we consider an experimenter, Alice, who's in possession of a closed time-like curve and a classical bit, which initially has value 1, where she sends back this bit in time to communicate with her past self how she will use the closed time-like curve, where the value 1 means I entered the closed time-like curve and the value -1 means I have not entered the closed time-like curve. And by sending the bit x back in time, she produces an older instance of the bit denoted as y. And Alice now enters the closed time-like curve only if her future self has not done so, and she does enter the closed time-like curve if her future self didn't. And you can see that this is a paradox from the network that Alice must use to prepare her bit y, or sorry, her bit x, where she uses the bit y, copies its value onto her bit x, and then performs a NOT gate on her bit so that her final bit has the value -y. And then, of course, we have to require that, because of kinematic consistency, -y and y have the same value, which is not possible if y is an element of the set containing 1 and -1. Now, it turns out that this is similarly impossible to write down in the Heisenberg picture of orthodox quantum theory. So if you assume the commutation constraint is true, then you cannot find an expression that preserves the algebra of the qubits while also performing this classical network, or the equivalent of this classical network that Alice has. So instead, I shall treat a case in which Alice is in possession of a non-commuting qubit that she sends along the closed time-like curve, where here I have depicted a space-time diagram of that situation. So there's a qubit Q1, which is sent back in time. I assume that the trajectory of Q1 is classical and given. And because we send the Q1 back in time on the closed time-like curve, it produces an older qubit Q2 at a separate location at the earlier time, t equals 0, where then the qubits interact on this interaction region G. And because of kinematic consistency, we find that the observables of qubit 2 at the initial time t equals 0 must be equal to the observables of Q1 at time t equals 2. And on the right-hand side, I should say, I've written down a network diagram for the same situation, where the qubit experiences a negative time delay of -2 units of time. So to show that if Alice is in possession of a non-commuting qubit, she can, in fact, resolve the paradox. Let us assume that Q1 is maximally non-commuting and that its initial Z observable is sharp with value 1, has definite value 1. And that we can generate the initial matrix representation of qubit 2 because we know what kind of gate that the qubit will perform, and we of course know the kinematic consistency condition. So the initial matrix representation of Q2 is determined by those considerations. And because we now basically that these qubits perform the network I showed before with a C0 and a NOT gate, we have to assume that there is some kind of reference qubit. And assuming that this reference qubit is there, which I can get into, I think, during the questions, because I'm somewhat short on time here, unfortunately. The C0 gate can be implemented by letting the generative motion of Q1 be as shown here. And if we simplify the equation, we find that this C0 is really some kind of rotation of Q1 about its x-axis by some angle phi. If we rotate Q1 by this angle and then through the C0 gate and then enact a NOT gate on Q1, we find the observables of Q1 at time t equals 2, which must be equal to the observables of Q2 at time t equals 1. And because this angle depends on the expectation values of the observables at time of Q2 at time t equals 1, we find a self-consistency condition for the angle, which has the unique solution that phi equals pi over 2. And it turns out that using this phi, we have a unique solution for the paradox. In other words, if these non-commuting qubits perform a C0 and a NOT gate on the closed time-like curve, then they evolve in a way that's completely kinematically consistent, and there turns out to not be any paradox. And here I've summarized how those qubits would evolve. So that is the end of my talk. To give a brief overview, I've argued that there's this constraint, this axiomatic assumption in quantum theory that's problematic, and I've developed the foundations of a theory which does away with that constraint, and shown how that theory of non-commuting qubits might be used to resolve paradoxes on closed time-like curves. So thank you very much for listening.